still correlated. In a small network, well, because if I has a link to J, J has a link to I, right? So in a small network, the extreme case is that there are only two nodes, and they're perfectly correlated. Because if I has a degree 1, then J must have a degree 1. Okay, but the correlation is going to be small in a large network, because I mean, I'm linked to Shuhan, right? There are lots and lots of people that our link is just, so this pair is just 1 out of n minus 1. And so the fraction is very small. Okay, so we're going to, since in this literature people are interested when n is big, so you can just treat the degree as independent. Okay, so then for large network size, so when n is very large, you can approximate the binomial distribution with Poisson distribution. And Poisson distribution is easier to deal with. So yeah, so two things. One is, what we just did is, this is a probability that a randomly drawn node has d links. But that is different from the probability that there are the number of nodes with d links is equal to this. Is equal to n times this. So the probability a node has d links. So now we can ask, what's the fraction of nodes that have d links? So that's what we want to know. What's the fraction of nodes that have d links? So if the degree for two randomly drawn nodes are independent, then the probability that one randomly drawn node has d friends is the same as a fraction. In the limit, that will be the same as a fraction that have d links. Okay, so for large network size, the correlation is small, and then you can treat the degree distribution on the network roughly as the probability distribution of degree of a randomly drawn node. And then you can approximate the binomial distribution with Poisson distribution. Okay, so then this will be the Poisson random network model. Yeah, so for Poisson network, random network model, this is the fraction of nodes with d links. Right. So here's an example. Yeah. Okay. So to use Poisson distribution to approximate binomial distribution, what you need is n goes to infinity, and the probability of a link is going to be very small, but you keep np, the expected number of links, roughly equal. So here is an example of p is 0.02. Yeah, p is 0.02, and this is a realization of a realized network. And this is this one drew. This is a frequency distribution of a randomly generated network. So let's see. So the point is that the Poisson approximation and the realized frequency is pretty similar. I want to look at this realized, this generated network. So this one is a forest. A forest is a collection of trees. So what is a tree? A tree is a connected network with no cycles. So there's only, a tree is a connected network such that for between any two nodes, there's only one path between them. Okay. So this randomly generated network has no cycle. So you can, there are not many links, so you can just kind of see that between any two nodes, either there are no paths between them or there's exactly one path. So this is a property we're going to use when we calculate the size of small components. So what we're going to use is that a small component, the property that a small component has a cycle goes to 0 as the network size goes to infinity. Okay, so this is Poisson network. And there's another model called configuration model. So the point of this model is that you may want to match some particular distribution of degrees. So the Poisson network, what you have is you can match the average degree. So the average degree in the actual network, you can match that to the parameter of the Poisson distribution. Okay, and then so what you let n goes to infinity, but then the p, so if you're fixing the average number of links, the average link, then as the number of people goes to infinity, the probability a link is formed has to go to 0. But sometimes you might want to fit not only the mean, you might have a particular distribution of friendship that you want to fit. So you might have a distribution of degrees. So like say some people say how many people have this many friends. So you might want to fit this distribution. So how do you generate a network to fit a particular distribution of degrees? And a configuration model allows you to do that. So this is how you generate a particular realization of using a configuration model. So what you do is you take a degree sequence. So if you write down the degree sequence, then you know how many people has how many friends. So you said, let's say you have a degree sequence 1, 1, 2, 2, 2, 3, 3, 3, 3. And then, so say the first 2 people has just one friend. And then the next 3 have 2 friends. And then the next, I will just write it down. So I1 has 1 friend, so you just write down 1. I2 also has 1. Just write down 1. And number 3 has 2 friends, so you write down 2 copies of 3. Number 4 has 2 friends, you also write down 2 copies of number 4. And then this is 1, 2, 3, 4, 5, 6. 6 has 3 friends. So write down 3 copies, etc. So for every person, every individual, so if it has D friends, then you write down D copies of it. Alright, so now what you do is you randomly pick 2. So let's say I randomly pick 2, okay, I1 and I6. Okay, so then there's one link. So I1 and I6, there's one link between them. And then I eliminate this pair. So 1 only has one friend, so he's eliminated, so that means he will no longer be chosen again. So I1 will only have one link in the generated network. Now let's randomly pick two people again. So let's say it's I4 and I6. Okay. So that means there's a link between I4 and I6. Right? So then remove them. Let's randomly pick again. So let's say it's I4 and I3. So there's a link between I4 and I3. Okay, create a link between I4 and I3. So now, so there you remove them. So you will exactly get 2. So now you no longer have I4. So you will exactly create 2 links for I4. Okay. So you do that until there are no more people. Yes.
But because it's random, would it happen like I4 pair with I3 2 times?
Yes. So it's possible. So because
But then there's
you might have duplicates. So when you do it this way, you might have duplicate links. So what they do is, and you also might have link to yourself. And we usually ignore links to oneself. We don't, when we talk about networks, we don't have self-links. So there are 2 ways to do analysis. One is to prove result. So to show that, well, what you care about in the limit holds for, they call this multi-graph. So you allow self-links and also multiple links between the same 2 people. So you can do, or what you do is you generate it and then you delete the multi-links and the self-links. So the actual frequency of distribution of degrees doesn't exactly match the degree sequence. But then you show that when n is very large, the actual frequency is close to the degree sequence. And so of course you need to make some assumptions about the degree sequence. So here we assume that well the degree distribution, so here for any n, there's, given the degree sequence, you have a degree distribution. And then, so we assume the degree distribution of the degree sequence converges uniformly to some degree with finite mean. And then there exists some epsilon such that the sequence contains no node of very large degree. So then, as n goes to infinity, the probability of multiple links and self-links will then go to 0. Okay, and then here is what you want is basically this is going to show up when we calculate whether giant component exists. So you want, basically you want we already said we want the limit, the distribution, the degree distribution converges uniformly to a distribution with finite mean and finite variance. So if the degree distribution converges to a distribution uniformly to a distribution with finite mean and finite variance, then you have So usually the question you ask is, say, given some probability distribution of random graph, so either a degree sequence or usually it's a limit of the limit distribution of the degree sequence, or the average number of friends in a Poisson network model. So given some probability distribution of a random graph model, how do certain properties change with n? So one question you can ask is, does a probability the network is connected converge to 0 or 1 when n goes to infinity? So, but this is unrelated to the paper we're going to talk about. Skip it. So let me say we're going to use the degree distribution and some slight variation of it. So PD is the probability of the degree distribution of random graph in the limit as n goes to infinity. So that is what we're going to, the distribution we're going to use. So if you randomly pick a consumer in a friendship network, the probability this consumer has D links is PD. Then we're going to rely on probability generating function of the distribution. So the probability generating function of a random, so you randomly pick a consumer in a friendship network, then the number of friends this randomly picked consumer has is a random variable. Okay. And it follows a distribution PD, that's just some given thing. And the probability generating function of this random variable, that is a randomly drawn consumer's number of friends, is this function. So it's the expected value probability mass function of some random variable x. Then the probability generating function it's a function of some number little x. It's equal to you sum over all possible value of x. Here's x. Here the random variable, I'll just use it. Here the random variable is d, and d is ranging from 0 to possibly infinity. Okay, so this is probability that this person has d friends times, this is just some variable, some number x to the power of d. So it's the expected value of this is just a number x to the power of d. And then you're taking expectation over the random variable d, and d follows the distribution p. So this is just a tool, but it's going to be very useful when we try to calculate the number of components, the size of a component. Okay. So if you randomly pick a person, then this person, the probability this person has d friends is just given by the degree distribution. So that's exogenously given in the model. Now, suppose what you do is you first randomly pick a person, then you follow his link, one of his links, and then you ask, what's the number of friends that his friend has? That's a different question. So first, you randomly draw someone, that's called I. You of friends that I have. So this follows the distribution PD. Now you say I has 3 links, 3 friends. You just randomly pick one of I's friends, let's say J. Then you ask, what's the number of friends that J has? Because you find J through a link, so the distribution of the number of friends J has is not PD. Why? Because someone who has lots of friends will be more easily drawn this way. Because when you find J through a link, what you're doing is basically, well, since you first draw I randomly, so what you're doing is you first draw a link randomly from all the links. And then you randomly pick one of the end, one of the 2 consumers to that link. And you ask, what's the number of friends that this person has? And you find this person by randomly following a link. Okay, so the distribution, so the probability that this consumer has D friends, let's call that P delta D. So if you randomly pick a link, so someone who has D links, he will be found D times more likely than someone who has only 1 link. So and then this is the average number of links, expected value of D. So the probability a consumer has at the end of a randomly drawn link has D friends is this. Yeah, so instead of PD is the probability of a randomly drawn node having D links, it's D times the probability of randomly drawn node has D links. It just says someone who has 3 friends will be 3 times more, someone who has 6 friends will be twice as likely to be drawn than someone who has 3 friends. Okay. So now what we want to ask is, say you first draw I, and then you find J. You first draw I randomly, and then you find J by picking one of I's friends randomly. And then what you want, you're not interested, so I is J's friend. But what we want to know is you want to find J, like J's other friends. We don't want to count I because we already picked I. So the random variable we're interested in finding is the number of J's friends excluding I. So what we want to know is the number of links J has, excluding the original link we used to find J. So then then the random variable will follow the distribution. So this P delta of D minus 1. Okay, so we can get the probability generating function of this random variable. The number of friends of this consumer excluding the original friendship. probability generating function of the distribution T. Then what is GP of 1? GP of 1 is just so it's here we're not counting. If there's a mass at infinity, then you won't count that. So it's equal to 1 minus the probability that D is equal to infinity. Okay. So it's just GP of 1 is the probability that this random variable D is finite. Okay. And then what is GP prime of X? It's just take this distribution, it's B times PD times X to the power of D minus 1. So if you plug 1 in, if you take first order derivative of a probability generating function and evaluate it at 1, then that's just expected value of D. So now we're going to calculate the size of small components. So the claim is that every small component in the limit is a tree. That's for any small component. Probability that this component contains a cycle will go to 0 as n goes to infinity. And here's the intuition. So if there's a cycle in the component I, in some component with size as I, that means you can remove some link in this component, and this component will remain connected. This set of nodes will still be connected. Okay, then you can remove a link, and you can think about the probability that this link exists rather than some other link, or not this one not existing. So conditional on one end of this link that you just removed. So this link, conditional on one end of this link is in component I. Probability that the other end is inside versus outside of component I is roughly, also if you think of the Poisson random network, then every link, so between a pair, whether a link forms is independent. So you think of, say, if you have one end of the link inside component, this component I, and there are SI nodes in this component, so the fraction outside, right, it should be, the 1 should be outside. Okay, so if you know one end is inside this component, if for the other end to be inside versus outside, the ratio of probability is roughly the same as the ratio of the number of nodes inside versus outside the component. But because this is a small component, so the size is bounded, so the fraction goes to 0 as n goes to infinity. So as n goes to infinity, conditional on one end of a link being inside component I, it's much more likely that the other end of the link is outside the component rather than inside this component. So probability of a cycle within a small component is going to vanish. Okay, so what does that do for us? So suppose actually what I'm doing is I can ask, well, let's look at J, and let's say if we cut this link, since a small component is a tree, that means if I cut this link, no one here, no one that is connected to J, not through I, will still be connected to I. So anyone that has a path that is connected to J without going through I, they're connected to I only through J because there's only one path. So if I cut this link, then there is a separate, then this becomes a component within the component. So what I can do is I can ask, well, what's the size of a component J belongs to? And then what's the size of what's the size of a component that K belongs to? And what's the size of a component that L belongs to? And then I know the size of a component that I belongs to. I add them all up. Okay, so this is, I can, okay, so if a network, if a component is a tree, you can find everyone this way. They call it expanding neighborhood. Okay, so now the way to calculate component size is the expected component size is you ask, let's randomly pick someone and ask what's the component, the size of component that I belongs to. To answer that, you can ask follow I's friends, or randomly pick a friend of I's. So then what you're doing is you randomly pick a link. So randomly follow a link and ask what is the size of a component that the end of this link has, excluding the original link. And the size of the component I belongs to is 1, because you have to count I, plus the size of a component J belongs to, and the size of component K belongs to, and plus the size of component L belongs to. So it's really D. So let's say S is the number of component, the size of the component of a randomly picked consumer. What is that? It's equal to 1 plus D. D is a random variable, the number of friends that this randomly picked person has, times S tilde. Let's say S tilde is the number of friends, sorry, not the number of friends, the component size, the size of a component. If you randomly follow a link and then ask what's the size of a component that this consumer belongs to, excluding the original link. That's called that random variable S tilde. Then S is, you can think of it this way, it's equal to 1 plus D. D is the number of friends a randomly drawn person has, times S tilde. Roughly. And then we're going to use probability generating function to embody this idea. Okay. Okay, so let's talk about the threshold for existence of giant component in a friendship network. let's use that idea. If you randomly pick a node, what's the number of components, the size of a component that node belongs to? It's 1 plus you add up the number of components, the size of the components of each of its friends, excluding the original link. Okay? So yeah, so let's see, you have this person